Math 2414, sequences, video 10, the absolute value theorem. This is pretty short and sweet. It's a theorem that says that the absolute value of the sequence's terms approaches zero, then the original sequence's terms must also approach zero. And it's important to point out that this only works for the number zero. It does not work for any other number. And the main reason it works for zero only is that zero is the only number whose positive is equal to its negative. In other words, zero is the only number equal to its opposite. So we're going to take a look at two examples, one where you can use it and one where you should. So let's start with this example. an equals -1 to the nth power times the square root of n over n plus 1. Oh, by the way, I should mention that the time to consider using this is when there's an alternator, because if you take the absolute value of an alternator, it's always equal to 1. So because of the alternator, the -1 to the nth power, the absolute value of -1 to the nth power is always equal to 1, because the -1 to the nth power is either 1 or -1, but either way, its absolute value is 1. So it's that alternator that suggests to consider what happens when you take the absolute value of this term, which is the absolute value of -1 to the n times the square root of n over n plus 1, but square root of n is positive for positive values of n plus 1 is positive for positive values of n, and as we've already mentioned, the absolute value of this alternator is 1. Because the absolute value of a positive number is itself, we can lose the absolute value completely, because we know the answer to the absolute value of -1 to the n, 1, times the absolute value of the square root of n, which is positive, and therefore its absolute value is equal to itself, and the absolute value of n plus 1. But because n plus 1 is positive, remember we're starting with n equals 1, then n plus 1's absolute value is just n plus 1, at which point we really don't need the 1 times anymore. So we're going to consider that sequence and look at its limit. Limit as n approaches infinity of the square root of n over n plus 1. Now you might start having thoughts of L'Hopital's rule, since both the top and bottom go to infinity. But why don't we play the same game that we played before, when we slid a limit inside a square root after tricking out the entire term to be under a single square root. Remember, the way that you put something under a square root that's not under a square root, the n already is under a square root, but the n plus 1 isn't, is you square it, and then you can slide it under the square root. If we were to expand the denominator by multiplying n plus 1 times itself, and by the way, I'm still catching you, some of you doing this, what I'm about to write is incorrect. When you square n plus 1, you do not get this. Stop it. Powers do not distribute across addition. You would have to write the n plus 1 twice, multiply it as a full problem, if you will, and get n squared plus 2n plus 1. Learn anything from me, do that, but you should already know that. But anyway, let's get rid of the n plus 1 times itself down there and just bring back its result, n squared plus 2n plus 1. And now we can move that limit inside the square root. So why don't we just erase the square root and put a gigantic square root over the whole thing? So doing two moves at once. And think about the limit of that rational function that I'm about to highlight as n approaches infinity. I would do L'Hopital, you could do L'Hopital's rule to that, because the derivatives are easy because it's polynomials. I'd never do it to square roots. Anyway, but if we just use the observations about the degrees, anytime you take the limit of a rational function and the degree of the numerator is less than the degree of the denominator, then that limit's going to be 0, because the denominator is growing faster than the numerator. So the thing in yellow becomes 0, which means our limit is the square root of 0, which of course is equal to 0. And according to the absolute value theorem, if the absolute value of the sequence approaches 0, then the original sequence approaches 0. So we can draw one grand conclusion here. Our original sequence does approach 0. So basically, without the alternator, it went to 0. So with the alternator, we get alternating values that get closer and closer to 0. Take a a look at one more example. Oh, it's here. There it is. an equals -1 to the nth power times n over n plus 1. Again, it's the alternator that suggests to consider the absolute value of the term. But again, since n is a positive number, n is positive, so is n plus 1. Their absolute values stay the same. But when you take the absolute value, they stay the same. The alternator's absolute value is 1, so 1 times n is 1. So the absolute value of this term basically loses here. And so now we take the limit as n approaches infinity of n over n plus 1. But you can L'Hopital's rule, you can observe the degrees, or you can multiply both sides by 1 over n. Whatever method you use to determine this limit, it's up to you. Since the degrees match, you can't just take the ratio of leading coefficients. 1 over 1 is just 1. That inside limit is 1. So what does that mean about this? The answer is, well, it doesn't mean converges to 1 because the absolute value theorem only works for 0. If you drop an absolute value, you get a sequence that converges to 0, then the original sequence without the absolute value will converge to 0. So what does this mean? Well, it doesn't mean convergence. Well, let me take that back. It doesn't guarantee convergence. But I think I can make a stronger statement that it guarantees divergence by oscillation. Because if you think about it, we can play the subsequence game. Think about this. When n is even, then the -1 to the nth power is 1, so it disappears. And so we're just looking at n over n plus 1, and that subsequence would approach 1. But when n is odd, we already know the limit approaches 1, but when n is odd, what happens to the oscillator? It becomes -1. So it approaches 1 with a negative, and so an approaches -1. And so by using that subsequence theorem that we talked about before, you have two subsequences that go to different places. The original sequence diverges by oscillation. So I'm going to amend the absolute value theorem and say that also, if the absolute value of the nth term approaches some limit L, which is not equal to 0, then if an has an alternator, gotta be careful. Then an diverges by oscillation. Wondering why I said and it has an alternator. If it didn't have an alternator, then they'd be the same sequence and go to the same place. But if you have an alternating sequence, and without the alternator, you converge to something that is not 0, then the original sequence does diverges by oscillation. All right, so what can we say about this? Let's just say diverges by oscillation. I want to wrap up this video with a stronger absolute value theorem. If an, in fact, let's be real specific. An has an alternator. And there are a variety of alternators. It can be that, it can be that, it can be cosine of pi n. It can be a variety of things. But let's just say that it's got a regular old -1 at the end times another sequence. And n approaches 0, then an approaches 0. But if bn, basically the sequence without the alternator, approaches a limit that is not equal to 0, then the original sequence diverges by oscillation. But only if it has an alternator. All right, and that's a good place to end this video.